It is my great pleasure to introduce Yanping Huang, who is a software engineer at Google Brain. He received his PhD from University of Washington, working on reinforcement learning and computational neuroscience. His main research interests include neural architecture search and large-scale machine learning infrastructure. Actually, I've read a lot of his papers on neural architecture search, but what he's doing, according to himself, is more impactful on large-scale machine learning and natural language processing and translation these days. His work is published in top-tier machine learning and computer vision conferences and journals, including NeurIPS, ICLR, CVPR, Triple AI, Neural Computation, etc. He also served as a program committee member for several top machine learning workshops and conferences, including NeurIPS, KDD, Triple AI, ICML, WWW, Neural Computation. And today he's going to be telling us about GShard, scaling giant models with conditional computation and automatic sharding. So Yanping, the floor is yours.
All right, thank you very much for the introduction. My name is Yanping Huang. I'm currently working with Google. Today I'm going to present the model scaling efforts in our team, and I'm going to also to show how model scaling can provide a positive impact on the society. So here we demonstrated a single giant model that can improve the translation quality across over 100 languages. And these results come from a diverse group. We are a group of more than 30 persons, spanning many teams in Google. So we do the modeling, optimization, and systems research. And we focus on practical problems. So in this talk, I focus the application on multilingual machine translation. And the title of this talk is GShard, Scaling Giant Model with Conditional Computation and Automatic Sharding, which is also the title of our latest publication in iClear this year. So I put a link in the bottom left of this slide. And I will share the slide later. However, the scope of this project is beyond a single paper. So I will describe in greater context in this talk. So in the past few years, we observed a new trend in machine learning research, which I call it here scale. Basically, if we throw more compute and more data in the model training, we can get better prediction and better generalization on the unseen data. So as this cartoon shows, the traditional way of statistical learning would be like improving the rich dimension and get the better kernel. But in the era of deep learning, we can just stack more layers. We just increase the model capacity of the neural network, and magically the model quality would become better in most of the cases, as long as we have abundant data. So let's look at some of the largest models since 2016 and put those scale into perspective. So a common non-scientific way to describe the scale of a neural network is to compare against the size of the brains. So here in the horizontal axis, we show the number of synapses in biological systems. And we also plot the number of parameters of artificial neural networks at the same plot with the same scale. So before the popularity of neural network, the number of parameters in machine learning models is quite small. So for example, logistic regression, boosting trees, supervised machines, they typically have thousands of parameters. But since the popularity of the deep learning or deep neural network, the number of training parameters in the model started to explode. So in 2016, for example, image models like GrassNet or AlexNet have millions of parameters. So that is a huge increase in the model capacity comparing to pre-deep learning era. And as a result, as a return, the quality of image classification also increased significantly. And in around 2017, large models like transformers started to dominate the NLP applications, and it also comes with a large number of parameters. So for transformer, the number of parameters is typically hundreds of millions. So that's where we hit a wall for scaling. So because with these hundreds of millions of parameters, we already hit the memory boundary of a single GPU device. So in order to scale further, a lot of model pairs and model libraries need to develop. So in 2018, we saw an emergence of many model pair library trying to scale the model beyond a single device. So an example include like Google's GPipe, OpenAI's GPT, Microsoft's Zero, and NVIDIA's Mastodon language model, and also T5. My colleague Collins gave a presentation in this Colloquium in this year. So the scale in this range is about 1 billion to 10 billion. And in this range, we continue to observe, like if we increase the model capacity, by making the model bigger and bigger, we can observe beta generalization error in NLP tasks. So with the availability of this library and with more and more GPU or TPU available, companies started to increase their models dramatically. So in 2020, so we saw the coming of GPT-3, which has 175 billion parameters. And in our work, we show a GShard machine translation model that has 600 billion parameters. But with all this effort, so even since we can scale the model to like trillions scale, we are still tiny comparing to biological systems. For example, cat has 10 trillion parameters, and our machine learning system is not there yet. So in this talk, I'm continuing to talk about how we scale models, and I would like to focus on the challenge we made when we scale the model. So it's not as simple as we just change a few lines of code showing like by modifying the model config, then we can scale. So there are a lot of challenge in a way. So I will describe in detail. And here's another figure showing like since 2020, since the pandemic, people are staying at home and trying to figure out how to scale their model. So you can see like past 2020, once with the availability of those model pairs and libraries, the largest machine learning models increased significantly from like 8.3 billion parameters to 600. So it's almost 100 times increase in just 1 year. But the motivation of our group is slightly different. So we are not going to scale the model for the scaling sake. So we actually have a better motive. So our motivation is to build a universal machine translation model that can crack the people in the world. So what do we mean by universal machine translation model? So concretely, we're trying to build a single model that can do the machine translation across almost all the language in the world. So here is the world map, right? So Google's mission is try to organize the world's information and make it accessible for everyone. And as we can see in the map, different people in different countries speak different languages. And although the internet is mostly dominated by English-speaking text, so we also have billions of users. For those countries, their speakers have little access to English contents on the internet because of the lack of translation data. So our goal is to build a single model that connects people all over the world so that they can have access to information, but with tools from machine translation. So here is the distribution of training data for machine translation. As we all know, for any machine learning models, we require training data for the model to learn something. So that goes to the translation model as well. And in order to translate every pairs of language in the world, we need those paired data. So basically, we need to have 2 pairs of training sentences representing the same concept, so that we can do the translation. We can know that, so for this thing, in English, the sentence is like this. And for a different language with the same meaning, the sequence of words is in a different order. So with this parallel data, we can fit into our machine translation model and let the model learn how to translate. So here we show the distribution of training data for a variable at Google. So we organize the words language in the horizontal axis. So we show like 100 languages sorted by the availability of training data. So on the left-hand side of this horizontal axis is the high resource languages. So that's like Spanish, French, German. They have more training data. They have more training examples from their language to English. On the right-hand side, those are low resource languages such as Hawaiian, which has very few training examples available. So for example, the lowest training example we have is less than 10,000, sorry, 100,000 examples. So 100,000 examples is merely the size of a dictionary. And on the contrary, for the high resource languages, the amount of training data can be as high as 100 million examples. So that's 4 orders of magnitude difference. So of course, the quality of the machine translation model is proportional to the availability of the training corpus. So we want to build a single model that works for all in order to transfer the knowledge from high resource languages to low resource languages. Otherwise, for those speakers of low resource languages, because of the poor translation quality, they cannot access to words information. And at the end of the day, we build a very large model, 600 billion parameters, and it can improve translation quality across all 100 languages supported by Google Translate, the production translate services. So the same axis, the horizontal axis is the same. It's the ID of the languages sorted by the availability of the training corpus. So on the left-hand side is the high resource languages. On the right-hand side is the low resource languages. And the horizontal axis represents the translation quality improvements. So we show like at 0. So when delta blue is a matrix of translation quality improvement. So the baseline here is the fine-tuned machine translation model training on a single pair of translation pairs. So that's the best we can get if we just train those language pairs one by one. So for each language pairs, we can train a dedicated model for this pair. And the baseline would be the best model training in this setting, the best bilingual translation model. And we can observe that by using more and more number of parameters in the model, we can improve the translation quality, especially for low resource language ones. So that's the main results of this talk. And then for the rest of the talk, I will talk about how we can get to these results and what difficulty and challenge we met during this project. And at the same time, feel free to interrupt me and ask me any question you might have. So let's start with the challenge we met. So on the left-hand side of this equation would be the quality of any machine learning system. And we know the quality of or the prediction power of a machine learning model. And the X here is the training data. So it's not like we cannot train anything. We cannot learn anything. So data is the most important. So in this context, the data comes from all the parallel data, all parallel sequences of the translation model for the translation. And theta would be the model, which is the model parameters and the model architectures. So because like different network wiring would significantly affect the quality of machine learning model. And mu here is the hyperparameters for the optimization. Because once we have the model and the data, we can start to use the optimizer and the learning rate to tune the model, to actually minimize the training loss. So those are very important as well, because like if we set the learning rate too high, for example, the loss won't decrease at all. And there are a lot of tricks to make the model learn, especially at the area of giant model. So the bigger the model it is, actually it's relatively easy to train, but we still meet some difficulty in the trainability. So those are three main aspects of a machine learning system. But oftentimes people overlook the importance of a crucial component, which is the systems. So it means like systems, I mean the engineering aspects of that, of the machine learning model. So that includes the ease of programming and distributed training infrastructure, model or data parallelism in order to make use a cluster of devices, and efficiency of model training. So that means how much time the devices are waiting for the input, or waiting for other components of the network. So that is also very important in the large scale systems, such as machine translation for all the languages. So here goes the overview of the talk. First, I will talk about data. Next, I will talk about the model. Then I will talk about the trainability and optimization. Finally, I will talk about the system aspects of this system. So first, the data. So here we show this training data distribution again. So we know that the total of our system has over 25 billion training examples. So one example is one sentence. And each sentence can vary from dozens of characters to dozens of words to hundreds of words. So we have very long sentence, because like the longer the sentence it is, the more context this sentence can present, and it can make the machine learning model underneath to be more context dependent. So because as we know, like the meaning of word green have many different, it's quite ambiguous. So depending on the context, the meaning of the green word differ quite a lot. So we need to provide context for translation as well, so that it can translate, so the model can translate accurately about the original meaning of the source language and generate corresponding words in the target language. So as we said before, the horizontal axis is the language ID or language pairs. So on the right-hand side is the high-resource language, such as Spanish to English, French to English. With the abundance of training data available on the internet, we can already approach human quality translation. Like Spanish to English is very good if you try it on Google Translate for most of the time. So at least you can get the main idea after you do the translation. But on the other extreme, for low resource language, translation becomes more challenging because of the small amount of parallel data. So 10 to the order of 5, so 100,000 examples for translation is tiny. So because in a language, a typical vocabulary would be 10,000. So there are 10,000 words in a single language. So that means just like there are only hundreds of pairs of examples for each word. So that's merely the size of a dictionary, bilingual dictionary. So how can we learn to translate sentence based on a dictionary? So that would bring this quality, that would make our translation quality for those language pairs quite difficult. So the idea here is that, so here shows the translation baseline quality if we just train our model based on bilingual data. So as we can see, on the left-hand side, the high-resource languages is very good. So the blue score is almost 40. So that means like it's almost at the human level. But on the right-hand side, the translation quality is quite poor. So we will use this baseline number, baseline blue, as our baseline. So that would be our horizontal axis. So that would be the 0. So we just plot this baseline scores into horizontal axis. And we will expect if we can combine those training data together and train a single model. So we will expect the data, we will expect some transferability from data-rich language pairs to data scale poor language tasks. So like this transferability would mean like there are suppose some universal structure in the language that would common across all the languages. So that what we learn from English to Spanish can transfer to our understanding of the Hawaiian to English. So that is the ideal case we want to aim. So we want to transfer the knowledge from those data-rich tasks to data-poor tasks. But in reality, we cannot observe this. So in the first attempt, we trained a single model, the same model as we use for bilingual translation. And with this single model, we just trained across all of the training data. And we did observe a large gain on the low resource languages. So transfer did occur for low resource languages. But because of the limited capacity of the model, we saw a decrease in the translation quality for high resource languages. So it means like there's some interference in this multilingual setting. So although we can see the improvements on the low resource end, there's those competition or interference in the high resource region. So we need to come up with some ways to conquer this difficulty. And that's why we go to the model scaling. So the model scaling is not just like we want to do giant model and let's try some applications. It's we first trying to come up with a model that is capable of all those translation tasks. But what we found is that there's a limited capacity in the current model that we need to scale up. So here, then we come to how we scale the model and what would be the model aspect of this project. So the model we are using is the transformer. So it's been explained by many different papers. So the basic idea is that the input of this model is sequence of word or the sequence of tokens. And with some embedding matrix, which map each individual word to a vector, a float of a list of floats, basically. And this transformer architecture will do some combination of matrix multiplication and nonlinear function in order to get the output. So the output of this model will be a sequence of list of words. The sequence of floats. So the input is the sequence of tokens, and the output would be a sequence of embedding. And each embedding is just an array of floats. And we don't need to go to the detail of this architecture, but there are two key parameters we can tune in terms of how we control the model size of this model. So one is the number of layers, what we call the depth. So the term deep learning comes from the number of layers in a network. So what deep learning shows is that if we stack more and more layers in a neural network, the performance becomes better. So that is a common belief. So that is the depth of this model. And there's also the width of the model, which is the model dimension or the embedding dimension of the floats. So that's like when we map the input token to some floats, some vector, and that is dimensionality of the vector. So these two aspects control the number of parameters in this model, in this transformer model. So as we showed before, if we just use the base transformer model, we show improvement in the low resource languages, but we saw the quality loss in high resource languages. So our hypothesis first would be like because of the limited capacity in the model. So let's increase the model a little bit to see if it improves our quality. But here comes the research questions. How do we scale? So we can go deep or we can make the model wide. And how deep and how wide can we go? And are those two ways the only way we can scale the model? and what other innovation we can make in order to improve the quality. So let's go to the first question. So can we go deep or go wide for the transformer model? So in this experiment, the light blue curve is the model we have before, the baseline multilingual model, which has the same size of the standard bilingual transformer. So the light blue curve has 400 million parameters. So let's increase the model size a little bit. So we control the number of parameters for the scale-up model, and we try two different ways to scale. One is to increase the number of layers. That means we want to have a deeper model, which is the blue one, the solid blue curve. And we also try to make the model wider, which is the yellow curve. And we can see both models perform well across all the languages. So especially they make the high resource language better. So that validates our hypothesis, which is the capacity of the original model is limited so that there are interference in high resource languages. So by scaling the model up, we can conquer those quality loss. At the same time, we can preserve the quality gains from high resource ones. But the difference between the deeper model and the wider model is how they scale for the low resource languages. And we observe here, like deeper model did scale well, scale better than the wider model. So from that on, we're trying to make the model deeper. So we continue to do it with 128 layer. So that is the 6 billion parameter transformer, which is already 15 times larger than the baseline model. So with this increased size, we can see a model that is better than all those baseline translation quality. So at the first time of history, we can build a model that's capable of translating all 100 language pairs and has better translation quality across all those languages. So questions so far? So feel free to ask me any question during this talk. And this model at the end went to the production system. So whenever you use Google Translate right now, it's using this model because it demonstrates from this test data sets that it performed better than all those baseline production model. And then Google Translate, the production system adapt our model for serving. So today, on each day, this model is translating billions of queries every day. But we call this way of scaling dense scaling because we just simply increase the depth of model or the width of model. So we just make the model bigger and bigger. And at the same time, each input token will touch the entire network. So the problem of this is that although we can see better translation gains by scaling up the model, we also saw an increase in the training time and the training cost. For example, in order to train this 128 translation model, it takes 5 weeks of training time. So that was way too long for a research project. And it's also way too long for a production project as well. So we need a smarter way to scale. So here comes the relative chip sparse scaling we invented. So we call it the mischief iceberg model. So the essential idea here is the so-called conditional computation. So unlike the dense scaling, where the input token touch the entire network, in conditional computation, only part of the network is activated for a given example. So if you think about it, for each example in the dense scaling, and we're going to activate the entire network. So the entire network is going to have some computation with this input example. But in conditional computation, because only subsets of the network is activated for a given example, so not all those parameters in the model are activated during the computation. So that would greatly reduce the training cost and the inference cost as well for the same number of training examples. So at the end of the day, we are able to train a 600 billion parameter model So comparing to the dense model, we can go up to 6 billion, and it took us 5 weeks to train. But when we scale the model 100 times more with this sparse scaling, it only took us 4 days of training time. So we get 100 times larger model, but our training cost is like 1/10 of the original dense scaling. So let me provide some illustration of the comparison between dense model and a sparse model. So in a training batch, suppose we have only 2 data points, 2 examples. For a dense model, each of these data points, each of those examples are going through all those layers. So for each layer, we are computing using these 2 examples for all those parameters in each layer. And at the end, we predict the output of those 2 examples. But in the sparse model, we can replace some part of the model with the so-called mixture of experts. So we call it expert layer. So we divide this model into common blocks, so which is shared by all those data points, and some expert layers, which would activate differently for different data points. So those expert modules, we can scale wildly. So we can make these common blocks the same size as the original model, but we can scale the expert module by 100 times. But because in this example, we have only 2 data points, but we are not going to activate all 100 experts in those expert layers. We only activate a subset of those experts. So at the end of the day, not all of those experts, or not all those modules in this model are activated, so they are not contributed to the computation cost. So hopefully this diagram would capture the essential idea of the sparse activity model. And that's the way we continue to scale our model while keeping the computation cost small. So that is back to the transformer model. So the common architecture among those expert module would be the attention layer. And what we replace would be the feed-forward layer of the transformer. But we don't need to go to the detail of this architecture, and the details is in our paper. So what are experimental results? We scale the model in a sparse way, comparing to the dense way. And we can show that in a simple example here, once we scale the model to 50 billion parameters, so that is the same model as before, but each layer we have 512 experts. And comparing to 128 experts. So if we add more experts to the expert layer, does that help translation quality? So we can see that by adding more experts in this model, we saw consistently better translation quality in the high resource region, in the high resource task. For low resource tasks, it stays almost the same. So that again validates our hypothesis that the quality loss in high resource languages is because of the capacity bottleneck, because of the lack of capacity for those high resource languages. And combining these 2 efforts, we can scale up to 600 billion parameters. So we can make the model deeper, we can make the model wider, at the same time we can make the model more sparse. I have a lot of experts in the expert layer. So at the end, we can scale the model up to 600 billion parameters. So comparing to our baseline model, which is 400 million, that is 1,000 times increase in the model scale. And comparing to our best dense model, we increase the model capacity by 100 times. But let's compare the quality. So with 100 times increase in the model capacity, we saw even better BRU score, so which is a quantitative matrix to measure the translation quality. So with the dense scaling, we can see 6.1 average BRU score increase for all those translation pairs. But with the mixture of expert, it will bring additional 7.4 BRU score gains for all the languages. And as we know, because we are approaching the human level translation quality, it's even harder to improve on top of the previous improvements. So on top of this translation quality gains, we also saw a reduction in translation in the training cost. So the end-to-end time to train the model reduced from 5 to 6 weeks to only 4 days. So the cost in terms of the TPU code years, that is the number of time. So because like we train not on just one TPU core, we train on 2,000 TPU cores. So we can measure the translation or training cost in terms of TPU core years and reduce the training cost by 10 times. And we can continue to scale the mischief expert or the sparse activated model further. So increasing from about 40 billion parameters to 600 billion parameter, that is a 16 times increase in the model scalability. We only increase the training cost by 4 times. So we can achieve sublinear training cost scale. So unlike the dense scaling, if we double the number of parameters in the dense model, the training cost would double because every part of the model, every neurons in the model will be activated during the training. So if you double the number of training parameters, you need to double the number of training costs correspondingly, given the same number of the experts. So the takeaway from the modeling aspect of this project is that first, deep model are more sample efficient, and deep model converts better. And if we can relax the capacity of the model for the high resource languages, we can see consistent quality gains. So the quality gains come from the capacity. It can be dense scaling or can be sparse scaling. And our 600 billion parameters is relatively cheap comparing to the dense model. It can be trained under 4 days and still achieve the best quality. And another thing we observe is that the deeper model is better at transfer towards the low resource languages. So that is the result from the dense scaling. So that's it for the modeling perspective of this project. So we learned that we can, if we scale our model smartly, we can increase the model capacity of model and bring the best machine translation quality to the users while not increasing the training cost. And next would be the trainability. So it's not just like we build a model system, we change the model parameter, and the model itself will just train automatically. So there are a lot of trainability issues we found training the large scale model. So the first part is still the data. So if you just combine all those training data together, actually we didn't see any gain. Because remember the data distribution of our training data. For the high resource languages, we have like hundreds of millions of training examples. For a low resource language, we only have hundreds of thousands. So that's order of it's 4 order of magnitude difference between high resource ones and low resource ones. So when we mix them together in a single training system, then the high resource languages would have more chance to be trained because they have like 10,000 times more training examples. So we cannot just combine them together. We need to sample the low resource examples more frequently so that they can have more chance to be trained. So that's how we did it. And after refining the data, so we've sampled less frequent for high risk models and sample more for low resource language pairs. We can observe this kind of transferability we showed before. So the green curve on the right would be the curve I showed before, the baseline multilingual translation model, without increasing the model capacity. So with some change in the mixture of the training example, we can see significant increase in the translation quality for low resource languages already. And another important aspect of trainability, of course, is the learning rate schedule. So that is the most important hyperparameter in any practical machine learning system. So in order to tune it, so we need to babysit the model. So we need to evaluate the model during the training time. So like we can observe the loss. We want to make sure the loss decrease correspondingly. if the loss fail to decrease, we need to change the learning rate to decrease the learning rate a little bit, and then we continue to train. So it's not as easy like we click a button and then the model runs. We still need to babysit, especially for the first time we're trying to achieve something, to achieve a better quality. So once we come up with the recipe, we can hard code this training learning rate schedule. But before we discover it, it still need a lot of like manual work to come up with the best learning rate schedule. It's not the best, it's just like the ad hoc learning rate schedule that works. So that is the unfortunate part of machine learning. That is still not automatic. That's not still fully automatic. So lastly, we are running almost out of time. I would like to go over the system aspects of this project, because because of the scale of the model, we are already have 6 billion parameters. So for each parameter, it would take 4 bytes to store. So the whole model would be a few terabytes already. So that already exceeds most of the memory for the desktop machines, let alone the accelerators. So in order to change such a big model, we need to distribute the weights across different GPU or TPUs. We need to do it in a distributed system way. So we use 2000 Google TPU to train such a big model, but we have to make sure this model, this system is scalable. So we want to make sure like even with model distributing on 2000 chips, we are as efficient as we train it on a single device. So that comes with a lot of hard work on software engineering and systems optimization. So because of the time limit, I don't have time to go to the detail, but we already open source our data, our framework on GitHub. Feel free to go into more details. So I put a link here. And another aspect of the software engineering is that it's very important to decouple the model config from the optimization. I mean, the performance optimization. So we want to write model code as we have infinite capacity of the, we want to write the model code as we have a strong enough computer, like has infinite CPU, have infinite TPUs, infinite GPUs, infinite memory. And then we we just want to insert optimization code that run this model codes on a distributed system. So it's better we separate these two system aspect of code from the model aspect of code. So it's just like writing SQL. So in SQL, we write our logic or compute logic in the SQL code. But under the hood is a lot of optimization for a distributed system. So we want to follow the same paradigm in giant language model or giant model training as well. So user just write high-level machine code, right? So we have a translation model, and we repeat this translation model many times to stack them together into multi-layer translation model. And then here's the input, here's the output. What would be the loss function? After the model, after the director define those model code, it will be up to the compiler or up to the TensorFlow or whatever machine learning infrastructure to optimize that for distributed system. So like the data scientists or machine learning experts don't have to worry about the system aspects of the problem. And in this way, we can make sure like our model is correct, right? Because a single change in the code would be a disaster. So because like it's very error prone if we just change the model code. Because like for example, you just suddenly change the learning rate schedule, then everything would become then. It's just some of the common lessons we learned during this project. And that shows like we can use Google Cloud. So like our training machines are all across the world, and you can train them in a distributed fashion. So that's all for today's talk. So now it's time to take questions.